Okay, so let's wait a couple of minutes for Salvador. Y ya llegó. ¿Qué tal, Salvador? Buenas noches.
Buenos días.
Días muy bien. Okay, so let's start now. So we will see a couple of things about flows and also the leaf bracket that we covered yesterday. So we have a vector field and wait. Right, so we have a vector field and a base point, a reference point P. And what we saw very well using the existence and uniqueness of ODEs was this result. So remember that this is the local flow, and local because that's why we make a reference point and we have a small neighborhood about it. And also, I forgot to use here the info between both of them. Remember that we don't have that for every t. We only have it for some t. So this is E only in some interval about the origin. Okay? So in principle, this is something very small. And also, I put a star there because to be strict, they are not diffeomorphisms, right? So I mean, if I put here the image of V, then these maps would be a diffeomorphisms, not of M, but of a smaller set. And the whole idea of this flow is put together all of the integral curves in the neighborhood of P. So this is the initial condition, because that's what we get from ODEs. And the whole idea is if I fix a point and I start to vary the parameter t, I have an integral curve of the vector field, right? And something that we also discussed using the uniqueness of the solution of the system of ODEs was this relation. Okay, now because this is a local flow, we have to be very careful about these three parameters. And also something else that I didn't wrote here, if you evaluate this at a point Q in V, so you have to make sense that also this is going to lie in V so that I can apply phi of t, right? So again, we would like to think of this as the inverse, but again, we have to be very careful what do we mean by the inverse, right? Okay, so this is the local flow that we discussed some time ago. Now, remember that we saw several examples, And just to illustrate this, in R2, we saw the flow going in one direction. In that case, remember that V was the whole space R2, and this was the whole reals. Also, we saw the example of the rotation. In that case, also M was the whole space R2, and the time can vary in all of the reals. So that's exactly what I want you to picture, because in those cases, we do in fact have diffeomorphisms, because here is M and M. Okay, so, and also because that is very important, when you can do that, those vector fields have a name. So we call that the vector field is complete if what I said holds. If we can take V to be the whole M, and the existence of these maps is for all T. Okay, so the example that I just mentioned on R2 are called complete vector fields. The one of the rotation and going in one direction. Right? Something that is not complete, remember when we remove one point, when we went going in one direction. In that case, we had something like this. We were not able to have the flow for all T, and also we needed a smaller space V. Okay, so I will focus on complete vector fields. And there is more or less something very easy to say when a vector field is complete. So as a function, we define the support of a vector field like this. The set of points where the vector field does not vanish. And if the closure of this set is compact, then the vector field is complete. Okay? So, for instance, if my manifold is compact, any vector field is going to be complete. Okay? For instance, the example that was going like this was also the complete vector field, right? Okay, so that's what we have. And so again, the whole idea that I came back to this is because I want you to understand flows. And so, although this must be clear to all of you, why do we have those limitations? That those limitations ends by a result in ODEs. But I would like you to think about this in terms of for every T, and here you can put M. Okay? So when we have a complete vector field, actually what we have, now I'm making this more precise. We discussed this some time ago. So we have this map. Remember that I said that we have like a path of diffeomorphisms. So this is a smooth manifold. You know this very well. However, this is something quite big. This is no longer a finite dimensional manifold. So you should think of this in terms of analysis, because that's like the most background that you have, a space of functions from M to M. Okay, so we have this, given a vector field. Now, so this is for HD, I have this. But remember the relation that we have. So this will go here, and we know this relation, right? Here, we don't have to worry about T, S, and T plus E be in some domain, because I'm assuming that the vector field is complete. So that works for any T. And also, I don't have to worry about T domain, because it is all of M. So I have this. And what is this? So what I'm saying is that this map is in fact a group homomorphism. So on the left-hand side, the reals using addition for the group structure. And on the right-hand side, the composition. You have the group structure on the homomorphisms. So a complete vector field induces a group homomorphism like this. And usually this is called the one parameter group of the vector field X. Okay? So in here, I have a very specific path. I have a vector, which is a vector field, and I'm obtaining a curve. And remember that I said that we should think of this curve, the image of this, like tangent to the vector. Okay? So that's what one way of thinking of this. And also, this curve is very particular because I have this relation. So it is not an arbitrary curve, but some particular curve of the homomorphisms. It's not any path. Okay, up to here, any questions? Right? Good. Now, going back to this, so again, I said that this is something familiar. You can do calculus or something about manifolds because it is a finite dimensional manifold. This is a space of functions, but I mean something that it is important either from the geometric point of view or from the analysis point of view. We would like to say that this function is continuous or smooth, although we have no information of here to say that it is smooth. But okay, it is possible to characterize this map as being smooth using only the concept that you have learned so far about manifolds. So the way is, instead of thinking of this map like this, let's think about it like this. in this case, on the left-hand side, you have a manifold. On the right-hand side, you have a manifold. So the regularity assumption that this map satisfies is that this is a smooth function. And this is something that you understand now, what it means to be smooth. Okay, we're here, so not very much because we haven't studied any structure here. So the whole idea is a complex problem. We look at it in a different way to something which is more easy to understand in terms of manifolds. So it so happens that this map, which is the one parameter group, is a smooth map here. Okay? Right. So this is what I just wanted to recall and stress about flows. Right? Okay. So at least this is what I just wanted to say. Now, let me say a couple of things also. Basically, this is oops, I didn't. Okay, now. So sometimes this is also referred as a dynamical system. So if you have seen those in one of your classes or in differential equations, so from a vector field, we are obtaining a dynamical system. Here, because we are doing manifolds, we care about this type of things. But sometimes also one have a discrete version. Discrete in terms of time. Okay. Phi n is a smooth function from a manifold to a manifold, but discrete in terms of time. You have time zero, the identity, and then you move forward and you can move backwards. Okay. So a continuous dynamical system, a discrete dynamical system, like the flow of this. And usually either continuous or discrete is time, and we are studying the evolution of whatever we are studying, the evolution in time. Okay, I don't know if there are any questions or comments on this before I switch gears.
No, it's all right.
Okay. Well, so Salvador, you said no? Everything clear?
Yeah.
Okay. Now, again, let's continue with this vector space. So this is a vector field. A vector space for any manifold, we have the set of all smooth vector fields. And yesterday we saw that this set has an additional structure, that it is an algebra. So we define the product of two vector fields. And it was called the Lie bracket. Now, let's consider a smooth map. And for a smooth map and vector fields, remember that under some conditions on the map, a vector field can be pushed forward. Vectors, you can always push forward, but vector fields, not always, right? So we have to be very careful to push forward a vector field. So sometimes when we can do that, has a name, and it is like this. So I have a vector field here x, a vector field here y, and I will say that they are f related if the vector field x can be pushed forward and is going to agree with y. Okay? Now, maybe here is important to exactly this. Okay, so let's remember what was the limitations of pushing forward a vector field. I mean, first, the left-hand side, this is not necessarily a vector field on N, because maybe the image of F is only this. So there are points in N that are not in M. So the vector field F star X and Y, they agree here. They are the same. That's what it means to be F related. And here the vector field Y, whatever, there's no restriction whatsoever. But on the image, both of them agree. That's what it means to be F related. So remember that in general, I'm not taking a vector field in M and obtaining a vector field in N. If F is a diffeomorphism, then that is true. Or for instance, if F is surjective and X and Y are related, then in fact F of X is a vector field, right? When this is the whole N and they are related, then F of X is in fact a vector field. So I just want you to be aware that this relation doesn't mean that it's an equality of vector fields on N. Okay, great. Now, I want to see this condition about being F-related a little bit more. So I have this vector x, I have this vector y, and what I'm saying is that under F star, this vector agrees with this one. So I'm going to write down that relation more explicitly. So this is a vector on n. So let's take a function and apply it on both sides. I have it here, okay? Right, because this is on x of p. When I apply f, this is a vector field on n at the point f of p. Okay, now, the definition of this, remember, is exactly this, right? Now, note that this is a number, right? Because I'm already evaluating. If I just put this is a smooth function. But I'm evaluating at this point, okay? So this is a real number. And a different way of writing this is like this. So this vector, this function evaluated at p, this function evaluated at f of p. But I would like both of them to be evaluated at p. So this relation is equivalent to this one. Okay? And I just have to evaluate at some point p in M. Okay? Remember that p is in M. Okay. Now, so let's see the following proposition that it is related to the Lie bracket that we saw yesterday and this concept of two vector fields being F-related. Right, so I have a smooth function. I get two vector fields on M, two vector fields on N, and they are F-related. The claim is, if I take the Lie bracket of these two, and I take the Lie bracket of these two, then those two vector fields will be F-related. Okay? So is the proposition clear for you? Now, I'm just going to write this. I'm going to put more notation just to make something clear, but usually we avoid this notation. So this Lie bracket is on N, and this one is on N, okay? There are Lie brackets, but they are happening on quite different manifolds. They are not the same manifold. Okay. Right. So let's see the proof of this. I'm going to take a function on this side, on n. And I know that these two are f related. So I'm going to write exactly this relation here. And the same for the other pair or of f-related vector fields, like this, right? So I know those two equations hold. And so let's push forward the Lie bracket and see what we get. Because that's what we are aiming at. We want the Lie brackets to be related under F. So here, I'm just applying the definition, right? This vector field is in M. When I apply this is a vector field, or, well, not a vector field, let's say a vector on N, and this function is on N, makes sense. This vector is in M, and this is a real function on M. Great, so we applied the definition of the Lie bracket. We have it here, that applied to this function and this function. Now, let's use this here, and we use this here, and we get that. Okay, here it is. Now I have x1 and I have y1. Great. Now, think of this as only one function. And let's apply this, right? This is a function. A vector field applied to a function is a smooth function. So we apply this equation here. So that's why this becomes the x1. This function is here. And then you have the f. The same here, I'm going to apply this. So I will get y1 applied to this function, and then composition with capital F. Okay, so far so good?
Can you explain again why the previous equality holds, in which you say that y1f it was one function?
Oh, okay, yeah. Right. Now, this comes from here, right? For the blue one. Okay, so let's understand this. Remember that we only have this, and this is any f. That's clear? So this holds for any function like this, right? Capital F is fixed. You cannot change capital F. But smaller f, you can put any function. Now let's go here. So this can be any function. Do you agree with this, Moises?
Yes.
Okay. Now let's go where we use it. Your question is this step, right? Okay,
Yes.
right. So I have x, and now you see this is a function g. So I claim that g is this function. y1 applied to f. And right, because y1 is a vector field on n, so this is a smooth function on n. You agree with this? Okay.
Yes.
So now let's apply the corresponding equation. So this is the formula that we're going to use. So I have x, I have a function g composed with capital F. Capital F remains. So what is? Write x1 with the function. This is my function g. And then composition with f. Composition with f. Does it make sense or not?
Yes.
Right? So I'm changing my function. It's no longer small f, but a different one. And the same here, I'm making this new function to be this one here. To get this. So if you want, so this is this vector applied to this function, and the vector y1 applied to this function. Okay? Great. Any other question? Okay.
No.
So let's continue now. So now I have this. Is this operator applied to this function composed with f? But this is precisely the Lie bracket. So it is this vector applied to this function evaluated at f. Right? So at the end, I have that this is equal to this. And we are done. Remember that this is the Lie bracket on m, and this is on n. And I now have that this vector and this vector are f related. Right? So we finish this proof. Any question?
No.
Okay, so okay, I mean, the whole purpose of this proposition was just so that you can exercise the concept of push forward or the F-related concept and the leaf bracket. That's basically the whole idea. Now, so let's be more specific. Assume that F is a diffeomorphism. So in that case, any vector field on M can be pushed forward to a vector field on N. Here we have no problem. So in this case, we do have something like this. Any vector field can be pushed forward to a vector field. So this is roughly speaking, that's a derivative. And the derivative are linear. So this is a linear map between this infinite dimensional vector space and this other infinite dimensional vector space. But that map is not only linear, but it is an algebra morphism. Because what we prove is exactly this, right? X is F related with F star X, because you can push any vector. So in the case of diffeomorphism, you have an algebra map. Everything fits together very nicely.
Algebra morphism is a mapping that preserves the product.
Right. So we have first the linear thing, the linear structure. So the sum is scalar product, and the algebra is the product structure, exactly. Right? I mean AB but here the product is the bracket, right? So you don't see the format as you are used to writing for the product. But this is precisely. Okay. Let me just leave it there so that you, yeah, I mean, you might be used to this relation, right? Oops. So this is what we proved in the previous proposition, but not for any A and B, because they were supposed to be F related. But if you are a diffeomorphism, you can put whatsoever. So this is the relation that we prove. It's the same as this one, but again, the product that we have uses a square bracket notation. Great. Now, I mean, also, we don't write x dot y because remember the definition of the leaf bracket is the commutator. And that's usually the definition of the commutator. You always use brackets. So that's what we have there. Great. Any other question? Okay, so let's move on. Yeah, the problem is that the Zoom and my menu, they mix up every time. So here. Okay, now I'm going to continue with the leaf bracket, but now for the leaf bracket, yesterday we saw a formula. And we use it here, right? I mean, here we use the definition of the leaf bracket. So we have that formula. But actually, the leaf bracket can also be computed using the flow. Okay? Again, this is going to be, I'm not going to put the details, but in order to compute this, we only need local information. However, I will treat the vector fields as if they were complete vector fields. No limitation on the time parameter and whatsoever. But everything is local. So we have two vector fields, x and y. They don't have to be complete. Again, I'm just saying that. And I take a point P. So here I have the flow or the local flow of x and y. And the whole idea is to give a geometric meaning because I'm writing down P, this is a vector or a derivation at P. So how can we compute that using the flow and not the formula? So let's make a function. And I would like to show you how this is computed. Okay? So this is P. So imagine that all of this is happening in a very small neighborhood of P. So phi of x and phi of y are the local flows. So for the time being, take any fixed value of t. I call it t0. So the whole idea is move along the flow with respect to x for a time t0. And then you reach this point. Now move along the flow of y for a period of time t0. And then we go the other way around. We move along the flow of x, but now the parameter is minus t0. And then we move along the flow of y, but along this parameter. and you might get here. Okay? So we always have the same parameter. Oh yeah, that is correct. And then minus and minus. Right? Now, the endpoint is close to P. Why is that? Why is it close to P? This is the function that I'm looking at, right? Now, what happens if t0 equals to 0?
We should get P, right?
Pardon?
We should get P.
P, right. All of this is the identity function, right? So when you plug in P, you will get P. But also note that that function is continuous. It's even smooth. So it is a smooth function. But okay, we only care about that it is continuous. So it is a continuous function. Then at P equals P. So nearby points of P are going to nearby points about P. Okay, so we are landing relatively close to this point P. As long as the parameter T is small. Okay, so we are doing this. And so the same that we saw yesterday, the whole idea of the Lie bracket is measuring if it's X and Y commute, right? If these two commute, regardless if D0 is 0, but if they commute, what happens? You get the identity, right? For any T. So the Lie brackets measure how much X and Y commute. If it's 0, they commute. If not, it is measuring how far is it from X and Y to commute. And you can see it here. If they commute, then this will cancel out and this cancels. Because it is the inverse. So if we plug in a function there, any function, the formula to compute this in terms of the flows is precisely that. Okay? I just plug in F just to make this limit in the reals, a limit of real numbers. If you remove the F, then you are taking this limit in the manifold, but I'd rather take it on the reals. Right, I mean, and also just keep in mind that there's some, so this is the right t, and here for some reason we need to take the square root of t. Oh, I forgot something here. Let me write it down. Because we are taking the square root, so we have to be careful on that. Right. Okay. Are there any question whatsoever about this?
I'm a
Everything
bit
is clear?
confused in the limit.
Come again?
I'm a little bit confused as to what why this limit is like this.
Oh no. Okay. Wait. I'm not claiming that this is a proof. I'm just giving you an alternative definition. It will require a proof that this is exactly what we have seen, right? I mean that this is so. I'm not claiming still this equality. I'm just saying to you, well, this is another way to compute uh, the leaf bracket using the flows. Again, because I want you to understand flows very well. But I'm not saying that this is a proof. I don't know if that was your question,
Yes,
Jesus?
yeah, yeah.
Yeah, okay, right. Yeah, no. I wasn't claiming nothing like that. Okay. Well, this is all that I have prepared for today. I don't have nothing more, so I thought this was going to take us a little bit more. Okay, so next week we will continue with the following. That's why I didn't want it to. Let's say. Okay. Okay. We have seen. I mean, in turn that we have proved many Lie groups. I don't remember. We proved this one, that one, and I think also that one, right? We proved that those are manifolds. Okay. Now, I told you what the Lie algebra is, but only has a object. It is the tangent space at the identity. But I haven't told you what is the algebra structure on that vector space. So this is something that we will see next week. And in fact, we will have a description of all of this. So far, we only know that they are subspace of matrices, right? Because either one of them, let's call it G, lives inside the set of all matrices. And so the tangent well, this is E is the identity. Oops. But you know that this is just the space itself. The tangent space in Euclidean space is the same Euclidean space. But we will give a description of what type of matrices we have here for each of these three cases. So far, we haven't said nothing whatsoever. So we will see what type of matrices do we get and the algebra structure that we are missing. Right? Okay, so we finished quite early this time. Do you have any questions or comments? Okay, then so I will see you next week and we will continue with, again, Lie groups and Lie algebras.
All right.
Okay.
See you then.
Okay.
Have a nice
Yeah, have a nice week.